Hello everybody, how are you doing? Nice to see you today. Last time we talked about the necessary condition of the extremum of the function. And today I finish with this theoretical part with sufficient condition of the extremum. So, sufficient condition of the extremum. So, I remind you that it is said that f of x has an extremum at the point x0 if the first one derivative of the f function with respect to x equals 0. I want to underline this condition with this red bar. We know that it is a necessary condition of the extremum. I put here necessary condition of the extremum. As you remember, we talked that if we even know that this point x0, at this point x0 function has its extremum, we can't define if it is maximum or minimum of the point. I remind you that schematically maximum or minimum and maximum look like these two curves. It's clear on the hunch. But what about sufficient condition? Look, let's make some define utter some ideas. Look, I use this blue ink to make schematically view of the maximum. So I have a rectangular system of coordinates, x, y axis here. And for example, this is the maximum of the function. And x0 here. Okay. So I want to add here some tangents line which touch the function curve of the function exactly at one point here. This is maximum. We know that here first derivative equals 0. And otherwise, if it is angle between tangent line and axis x, tan function of alpha equals 0. So these two equivalents. Then function first derivative of function equals 0. It's the same that tan of the alpha angle between tangent line and axis x equal 0. If I put here this one, draw here this tangent line x1, I denote it. You can notice that the angle between axis x and this tangent line, I do not like alpha 1, is an acute angle. An acute angle. For this part, I want to continue this axis x and denote it like alpha 2, and here x2. We can note that it is an obtuse angle. An obtuse angle. And the value of tan function is negative. Here it is like positive. Not alpha 1, but tan of alpha 1. Positive. What does it mean? How do you think? I want to add one scheme here. I use the red ink to distinguish these two situations. I can add xy system of coordinates. Xy. This blue curve is a function f of x. And here I want to make schematically view of the. It's not very convenient because my acts to be x here. Here I want to make very schematically, to draw very schematically function, the first derivative function. You can take into account that derivative of the function is a function as itself, because it's still mapping x into y, in some y. So it's function and its own graph. And look, what do we have here? If I denote here x0, x2, and x1, you can notice that this function, derivative of the x, it is kind of positive at the left side of the x2, and negative when it is x2, because tan alpha 2, and it crosses axis x at the point x0. Since that, it is kind of in decreasing function. A decreasing function if I add here if x0 is a maximum. So we can say that since that function f of x has a maximum at the point x0 if the first derivative of this function at this point x0, I didn't put x0, equals 0, and derivative of the function is decreasing function. But what does it mean decreasing function? If we calculate the second derivative of the f of x, if function first derivative is decreasing function, decreasing, yeah, then we can say that the second derivative is negative. Answer, we got to the basic idea of the sufficient condition. I want to frame it with the red ink. Finally, the very last definition. We can say that f of x has a maximum at the point x0 if the first derivative of the function at this point equals 0, and only when the second derivative is negative, less than 0. So, as a conclusion of this lecture, of this short lecture, brief lecture I can say, I give you I want to write down two criteria here. So, Extrema. F of x has an extremum at a point x0 if f of x0 equals 0. And it has maximum, minimum, if the second derivative at this point x0 is negative and less than 0, and if the second derivative of x0 is positive, function has minimum. By the way, this is the second one thing here. By the way, this is the guidance. How can we define if function f of x has extrema, and if it has, we can define are they maximum or minimum. And we have the only last one situation. What happens when f of the second derivative of the function at the given x0 point equals 0? Here we have some problems. How to say it? It can be maximum, it can be minimum, and it can be an inflection point. Maximum, minimum, or inflection. Inflection. If the first one derivative keeps its sign for both, then we can say that it is maximum or minimum. We have either maximum or minimum at this point. If the first derivative changes, second derivative. Second keeps its sign at this point, we can say that it is maximum or minimum. If the second derivative changes its sign, it is an inflection point. Or we can say here that first derivative of x keeps its sign No, it's done. Okay, but we can say, so we have the second derivative keeps its sign, or we can say that the first derivative changes its sign. Here it's keeps its sign. So we have kind of switching here. The second derivative changes its sign. First derivative keeps its sign at inflection points. For the maximum minimum points, we have the inversion situation when second derivative keeps its sign but first changes its sign. So you can use one of these criteria. You can investigate the second derivative, if it keeps or not, or the first one. So they work both properly. It will be clear, more clear when we calculate some examples. Okay. See you later. Bye bye.